folks, and welcome to another video. This one is going to continue our discussion with powers, roots, and radicals. And specifically here, I'm going to talk about the properties of rational exponents. And when you're done with this, you should be able to use the properties of rational exponents to evaluate and simplify expressions. So first off, we need to just remind ourselves, what do we mean by a rational number? Well, simply put, it's a number that we can write as the ratio of two integers, like 3/4, or -2, or 5/2. Numbers like that, what we call the nicer numbers. Stuff like the square root of 7, not rational. Pi, not rational. So we're really just going to be dealing with these types of numbers as we go through our lessons today. So here are your properties of rational exponents. And I'm just throwing these up here. These are right from your book, by the way. Because they're the same properties that we have with integer exponents. For example, the first property here says if we multiply with the same base, well, what do we do with their exponents? Well, we add them. Well, that's true with whole numbers as well, with integer exponents. So that still applies over here. If you notice, base 3, we're going to add those exponents, 1/2 plus 3/2, and we get 3 to the 2. So all these other rules that we have out here that we had for integers work for rational numbers as well. So you can take a look at these. You might want to pause it here, but I'm going to move on and actually do some examples with this stuff. So let's get some practice here. Well, in my first example, I noticed that, well, I'm using actually that first property that I just pointed at. I'm multiplying, and we have the same base. Both bases are 5. So what can we do with those exponents? Well, we can add it. And I'm writing it out like that just so I know and you guys know what I'm doing. But really what I need to do is change that 1/2 to 2/4. And then I can now add those exponents and write this as 5 to the 3/4. Okay, moving on to the second one. Well, these aren't the same base. So I can't just add those exponents together. What can I do? Well, if you notice, both of these terms are being raised to the 2 power, right? So I can distribute that 2, if you will, that squaring to both the terms, and I can write this as 8 to the, well, 1/2 times 2 is 1, and 1/3 times 2 is going to be 2/3. So I'm going to get 8 to the 1 times 5 to the 2/3. And I particularly like this column because that's really all we can do. And we get 8 times 5 to the 2/3. What we cannot do, what we're not allowed to do here, is actually multiply these two things together and get 40 to the 2/3. That does not work. Try to calculate if you like. See if you get the same thing, 8 times 5 to the 2/3 and 40 to the 2/3. You should if you put it in properly. Anyway, so this idea of leaving it the way it is, we get that a lot. I see people trying to put those together quite a bit. Okay, so on to the third one here. 2 to the 4th times 3 to the 4th to the -1/4. There's a couple things that we can do here. I certainly can take my exponent out here and distribute across the multiplication here. That would be fine. There's nothing wrong with that. I'm just going to do this a little bit differently. If you notice, we have the same powers, same exponent inside the parentheses. So what I'm going to do, actually, is I'm just going to rewrite the outside stuff first, is I'm going to do the power, the product of 2 powers in reverse. So I'm actually going to write this as 2 times 3 to the 4th power. You see how I did that? Normally we start here on the green and we would end up going that way, right? By distributing that 4. I'm actually going to go the opposite direction here. And what that lets me do is write this as, well, I can do 6, 2 times 3 is 6, and I get 6 to the 4th, and that's all to the -1/4. And now I can do my power to a power rule and say, okay, this is going to be 6 to the 4 times -1/4. I get 6 to the -1, or 1/6. So you should get that whether you did the method that I did, or if you distribute this -1/4 first. But I think you're going to have to do this property anyways, this product of two powers along the way either way. So whichever way you're more comfortable, it really doesn't matter in the long run here. Okay, two more and then we'll move on to some other stuff here. Well, this is really 7 to the 1, and this really is an old property that we saw with integers, where we can, with the same base, right, we can subtract those exponents when one's in the numerator, one's in the denominator. So I'm going to say that this is 7 to the 1 minus the third, or 7 to the 2/3. And that's a nice simple one. There's really nothing else getting in our way there. Okay, last one of these. Well, this one's a lot like the third one that we did, in that we have the same exponent here. Again, these are both being raised to 2, but this is going to emphasize my point of that we've seen before, simplify before you move on. So because these are both to the same power here, what I'm going to do is I'm going to write that as all of this stuff to the 1/3. In other words, this is going to be 12 over 4 to the 1/3. Again, that's that quotient of two powers in reverse. Again, so we're kind of undistributing, if we will. And then, of course, and the whole thing is it's the 2. So what this lets me do, again, you can see what I have here in red. That's just 12 over 4. So I'm going to have 3 to the, well, 1/3. And that's all to the 2. Okay, well, that's, again, power to a power. So I can say this is 3 to the 2/3. And we're not necessarily getting nice answers here, what we call nice answers. But there's nothing else I can do with this. That's as simplified as we can get. And that's one of the things we're going to see as we move along here. How do we simplify as we go along? So we saw back in the first session that we know that radicals and exponents are really just two different forms of the same thing. So what holds true for exponent properties should hold true for radical properties. So I should be able to multiply terms that have the same index. So I'm going to do just that. This is going to be the cube root of 5 times 25. Now, I'm going to write it like this, just so we see what's going on here. This is really 5 times 5 times 5, right? This is really 25 here. So I can write this as the cube root of 125, but actually what I'm going to do is I'm going to write this as the cube root of 5 cubed. You see why I did that? You see how I did that, first of all. And now you see why I did that, hopefully. I'm cubing the 5, right? I'm cubing the 5, and then I'm taking the cube root. So hopefully you see those as inverse operations. They undo each other, right? So I'm going to get that 5 here. If you don't like that idea, just go back to the beginning here and say, okay, well, this is going to be the cube root of 5 times 5 is 125. And now you need to know that the cube root of 125 is 5. So you pick which way you find easier. It might be a little easier to think in terms of the factors, which is why I showed you guys that. Okay, second one here. We're doing the 4th root of 162 over the 4th root of 2. And again, this is the same idea as we can do the same properties with radicals as with exponents. So these are both index 4, right? These are both 4th roots. So I'm going to combine this into not 3rd root, 4th root of 162 over 2. So I can put those separate radicals together. And now this is going to be the 4th root of 162 over 2 is 81. And now, can I figure out what the 4th root of 81 is? Well, 81, I know it's 9 times 9. Well, that's really 3 times 3 times 3 times 3. There's 4 of them, right? Okay, so that means that this is really the 4th root of 3 to the 4, which is going to be 3 to the 1, or just 3. Okay, so we're going to do one more topic here, and then the rest of this lesson is going to go on to the next video. So we're going to write radicals in simplest form, and I'm going to start off with simplifying the cube root of 54. So previously, we did stuff like simplifying the square root of 20. And if you remember how we did this, we broke this up into two factors, and I want to think of, okay, what's the largest perfect square that goes into 20? Well, the square root of 4 goes into the square root of 20. And then the other factor would be the square root of 5. And then we said, okay, let's actually do the square root of 4. Well, that's 2 times the square root of 5. And that's how we simplify the square root of, let's say, 20. So I'm going to do a similar thought here. Let me just move this out of our way. Maybe. Okay, I'm just going to move that out of the way. And I'm going to break up the cube root of 54. But when I do this, I'm going to think of what's the perfect cube root. That's a factor of 54. Well, you need to know your cube roots. Okay, so you'll get there. We'll get there eventually. But anyways, the 27 goes into 54, and that's a perfect cube. And the other factor would be 2. So I know that the cube root of 27 is 3. So I can rewrite this as 3 times the cube root of 2. So you take a moment, try to simplify the 4th root of 80. I'll pause this, and then I'm going to just keep continuing here. Okay, so what I'm going to do here is I'm going to think of, okay, 2 factors. I want to think of a 4th root that goes into 80. Well, what are my 4th roots? Well, 1 to the 4th is 4, okay. 2 to the 4th is 16. Does that go into 80? So it turns out it does. So I can say that the 4th root of 80 is the 4th root of 16 times, well, 16 times 5 is what gives me 80. And now remember how we got this 16 there. Well, the 4th root of 16 is 2. So this ends up being 2 times the 4th root of 5. So a little bit of simplifying for us there. So continue, watch the other video that I put online. It's going to pick up right where this one left off. And hopefully that's useful for us as we move on here using rational rules, for exponents and for radicals.